Hello! This video is going to be on section 2.1, and we will be talking about, hold that thought, the lords of data. Let's go to the PowerPoint. Here we go. Put this in presentation mode. And there we go. Okay. So let's talk about data. So chapter 1, we talked a lot about vocabulary words and kind of getting our foundation set for building upon all of the meanings between population versus sample, parameter versus statistic. Those are very, very important words that need to be fully understood in order to get through future word problems that we will be coming in contact with. Okay, so let's talk about the scientific method. A lot of you may have heard of the scientific method through your science classes. And the scientific method essentially is also used in statistics because we are still conducting experiments. We're collecting data and we're analyzing the data. And sometimes the data does come from an experiment with live subjects, human or otherwise. So the procedure for the scientific method is to first gather the information that you want to gather information on what you're trying to study. So if you're trying to study a dog's behavior when you ring a bell and then feed him and try to see if when he hears that bell, he automatically salivates in order to start eating because he knows the bell means to eat, then you'd be gathering information of your observing all of your observations of the dog after you ring the bell. Or if you are, let's doing a new drug test, maybe you have a better drug for a particular disease out there, then you will be gathering information on the effects of the drug on your trials, whether it be rat trials or human trials. Okay, then you want to take that data and formulate a preliminary generalization or hypothesis. So a hypothesis is your educated guess. You're going to want to make some decision about the data, about what you think the data is going to tell you. Then you're going to want to collect further data to test that hypothesis to see for sure if you are correct in what you hypothesized. If the data and other subsequent experiments support the hypothesis, then it becomes a law. Then you say, oh, now I know this, not just I'm guessing. Okay, but throughout the process, there are things called confounding variables. And these are really important for us to be aware of. So confounding variables are extra variables that are not accounted for during the experiment and can affect the results to the point where it's very difficult to know the difference between was this an increase in my results because my experiment worked, or was there some outside factor that got in the way? So, for example, let's say that I have a coffee shop and I decided to close it down for a little bit, remodel the whole interior, make it beautiful, make it modern. But then in my grand reopening, I'm booming with business and I'm like, this is fantastic. But up the street, a mall just opened up at the exact same time that I did my reopening. So now that's a confounding variable because I am unsure if my booming business has to do with my remodeling or if it's also affected by this outside variable, the mall opening up. So decision-making method. The procedure would be to first clearly define the problem and any influential variables. So in order to attempt to avoid confounding variables, you have to think of, well, what could possibly affect my experiment results? So if you're doing a trial on trying to quit smoking and you're having your subjects try your new quitting smoking nicotine gum, well, what if you were doing this type of experiment, you have to consider a lot of things. The personality of your patients, the other habits of your patients, whether they abuse alcohol or other illegal drugs, whether they eat healthy or not, whether they have, how many kids do they have, how much money do they make? all of these different factors, stress and eating and your health and other underlying issues you might have genetically, these can all affect the outcome of this nicotine gum helping a person to quit smoking. So when you're designing an experiment where you have all these kind of variables that will definitely affect your results, you have to consider them when designing the experiment itself. So you need to also decide upon objectives and decision criteria for choosing a solution, create alternative solutions, compare alternatives using the criteria established in the second step. Okay, so essentially, you really want to make sure that it is clear what it is you are testing, to make sure that you know what your target population is and that you don't go outside your target population. We were talking about in chapter one how if you targeted college students, you need to make sure that you don't survey the faculty members because they're not in your target population. So everything needs to be clear and you need to follow your defined experiment and your variables. You need to implement the chosen alternative and check the results to make sure the desired results are achieved. So everything is about testing, gathering data, rechecking the data, making sure that we have statistical significance, that what we were trying to accomplish was completed. So essentially, there are two ways to obtain data. You either do an observational study or a controlled experiment. Okay, so the observational study is when we do, actually, there's really no observational study or experiments. So, an observational study, there's actually two ways to really look at it. You run observational studies when you are trying to observe somebody's natural behavior. So, for example, if I wanted to know how many people really wash their hands after going to the bathroom, if I did it as an experiment where I told the subjects I was watching them, I'm pretty sure it's very unlikely that they would naturally just walk out of the bathroom without washing their hands if they knew somebody was watching them. They would be more likely to wash their hands knowing that that's the desired behavior of the person who is doing the experiment. So, in order to really accurately gauge how many people actually wash their hands, it would have to be done as an observational study where my subjects are not aware they are part of something. And I am just simply observing what they would normally do. Now, that experiment would be kind of creepy to be an observational study. I'd have to stand there in the bathroom and try to not look obvious. But it's a really good example for you to understand why you would need to do an observation versus an actual experiment. So, in an experiment, you would need the subjects would definitely know they're part of it, and you're telling them to do some sort of treatment, either take some pill or chew some gum or run 4 miles every day. So there's some sort of treatment applied on your subjects versus the observational study. You might put $100 bill on the ground and then stand back and watch and see what people do. So yes, you put the $100 bill, but you didn't apply that treatment on your patients. Your patients are just walking by what you set up and then you're observing their behavior afterwards. A survey would also be an observational study. So you're observing their responses. You are not influencing their responses. And when you set up a survey, it is so important to be careful of the way you word the questions. So, wording questions, if I said, do you believe in abortion? Do you believe in killing babies through abortion? Now, the way that I worded that question, I am hinting that I feel some type of way about abortions by making it gruesome by stating you're killing babies. So if I worded it that way, I may make somebody feel uncomfortable and they might step back and answer differently because I'm pushing them in a way. Or if I said, are you going to vote for Trump again? Because he makes America great again. Or say something where I'm using Trump's name instead of saying, in general, would you like to share who you would be voting for this upcoming election? Now, you see how general that question was, where I wasn't hinting one way or another. And just to be clear, none of the ways I was hinting was necessarily how I feel. They're just examples for the class. Okay, so data collection method is related to the nature of the problem to be solved and the ethical and practical constraints of collecting data in some experiments. So, for example, there are many cases where a simulation, which is another way to collect data, and a simulation is more like an experiment, but you are simulating the experiment versus actually using human subjects. And there's many reasons why you'd want to do a simulation. And one of the main reasons, or two of the main reasons, is either it takes too long to do it as an experiment, or it's too dangerous to do as an experiment. So, a good example of it takes too long is back in the 1970s, China was having an overpopulation problem. They limited every family to one child per family. Now, in the Chinese culture, having a boy is extremely important to carry on the family's name and to keep on with the family business. So, back then, there were female babies being thrown out in trash cans or given up for adoption as they wanted to pretend as though they did not have their first baby yet and that they wanted that boy. Now, you might be thinking, well, why didn't they just keep having babies? How is the law going to force you to only have one baby? But you have to keep in mind that Chinese culture is much different from the United States, and they had many different ways to enforce this law, such as you couldn't get promotions at work, insurance, and just the stigma the family would carry if they walked around with more than one child. So let's say you wanted to do an experiment on, well, what if we allow families to continue have babies until their first boy? Would this be detrimental to our population problem, but solve the female baby problem? If we did this out in real life, we would have to get 1,000 women pregnant. Not everyone's going to get pregnant. It's going to take years to get them all pregnant. We have to follow them through their pregnancy. Not all of them are going to carry to term. Then those who have boys would be done, but those who have girls, those exact same women would have to get pregnant again. So this would be decades long experiment. And by that time, your population problem might be completely different, or you just might not even have a country anymore. So that would be a situation where longevity is the issue, and you would need to do this through an experiment, a simulation. If I was trying to test airbags in a brand new car, I would not want to put a human behind the wheel and say, drive 100 miles an hour into this brick wall. Let's see if my airbags save your life. If they don't, I know I need to tweak them. Unsafe. So, in unsafe situations, you have simulations. They have dummies with sensors, and then the car goes 100 miles an hour into that brick wall. The dummy takes all the beating. You take the chip out of the dummy, and the computer would tell you whether the injuries the dummy has experienced would have been fatal to a human. So, many cases, collecting data needs to be done in a simulation type setting. Okay, so the conclusions suggested by statistics can be no stronger than the quality of the measurements which produce the statistical evidence. Fuzzy or confounded measurements must produce fragile conclusions. So, what does this mean? This means you just have to be careful with the experiment, and you can do everything right in how to set it up, but life still does like to surprise us. And if we know there were confounding variables that may not have been managed very well in your experiment, you just have to keep that in mind when you're building your conclusion. You don't want to be so hard and factual and saying this is definitely 100% the answer if you know that the data is a bit fuzzy, that it was collected with noise, as we like to call it. Noise means that there were some things that could have affected that data and therefore could have affected the results, and we're not 100% sure that this is all accurate. Now, a response variable measures the outcome of interest in a study, while the explanatory variable causes or explains the change in a response variable. So, for example, if I was testing the levels of caffeine and how many miles somebody could run, then my explanatory variable would be the caffeine, and my response variable would be the count in the numbers of miles that they've run. Let's take a look at this example. So suppose a new species of tomato has been genetically engineered to increase yields. How can we measure whether the new species produces higher than the old species? Okay, so in this experimental design, the plots of tomatoes will be divided into two groups. One that contains the new species and another that contains the unaltered variety, something that's known or has been watched over a long time. So we know what to expect from that variety. The plots contain the genetically engineered, the plots containing the genetically engineered, there we go, variety will be the treatment group, while the plots that contain the already known variety will be the control group. So that's a really important concept, control group. Okay, if we don't have a control group and we just filled every single one of the plots with this new chemically and genetically engineered variety of plant, then how do we know that it produced more? We have nothing to compare it to. Same thing in drug trials. If you're trying a new drug on your patients, how are you going to know if it did better than the one that you already have if you don't have comparisons? Using a control group also helps alleviate those confounding variables. So when you have the two groups who are also getting the same amount of light, the same amount of water, the same amount of beetles that might be eating their leaves, then you know that those variables are affecting both the control group, which you know what the expectation outcome is, and the new group that you're trying to compare it to. And then if the new group does produce more tomatoes, you know that these genetically engineered plants are indeed superior to the original standard variety. So if the experiment is properly performed, any change in the response variable can be attributed to the explanatory because you have that control group. Variables like rainfall, sunshine, the type of soil, all can affect your plant's growth and producibility, and therefore you need to keep those consistent. These variables must be controlled so that the differences can be explained by the new plant versus the standard. One possible method of controlling for these variables is to create these small little plots or use little pots and use the same soil, make sure that they're all in the same type of lighting, they get the same hours of light a day, and the same amount of water. Okay, so several plots of each type of tomato are planted. Rainfall is measured and make sure it's equal. By controlling for these variables, we are doing a very good job of making sure we can directly compare the producibility of the new genetically engineered plant and the standard plant. Does an SAT prep course improve performance on the SAT? So this is another example. Let's say this is a question you want to answer. So where do experiments come from? Experiments come from a question. So typically we have some question in mind that we would need or we desire an answer to. And that initiates beginning an experiment or an observational study, collecting data, analyzing the data, reproducing the data, and so on. And this completes the process. So a group of high school students take the SAT. Then they are given an SAT prep course. They retake the SAT. If the group's second SAT performance improves, then it may be related to the prep course. The explanatory variable would be the prep course, and the response variable would be the scores. So before would be the control group. So notice instead of the tomato plant, where in the tomato plant problem, we had the control group running at exactly the same time as the standard group. Here, our control has been done with every single subject. And then we apply the treatment of the prep course, and then they retake the test and they're compared to themselves. So why would we do the control group differently this time? Well, let's think about this. We are human. We all have different learning levels. We all understand material different ways. So how can I compare my SAT scores with a prep course to a completely different person's SAT score without the prep course? How would you know that I did better than that person because of the prep course? Maybe I would have just done better on the test than the other person, period, without the prep course. So because there's too many variables from one person's brain to the next, we are doing a good job by using the same group of people as the control group so that you're comparing one person's scores to his or her own scores, which is a much better comparison than trying to compare two different individuals when it comes to test scores. And that's pretty much what this is saying. Okay. Could you assign any difference in results solely to the SAT prep course? Well, I mean, you still have the issue in the fact that if this was the first time that they took the SAT as the control group, then maybe they needed to get their jitters out of the way. And the second time, they would have naturally done better because they're not as nervous this time. So there are still some variables that would need to be worked out. And repeating this experiment over and over again with new groups will definitely help to kick out any of those leftover confounding variables that you need to neutralize. So, because of the potential differences in the cognitive abilities of the two groups, as I was saying, it's important to compare a person against themselves. Now, a placebo is a fake treatment that has the potential to cause a response. So, for example, let's say that we have multiple sclerosis. So, MS is a disease that affects the body differently from one person to the next. And as of right now, there is no cure. Um, Most cases, people live just fine through their lives with MS. In some cases, it's fatal, but it's rare. And I know this since my cousin, who is in her early 40s, has just recently passed away from MS. She got one of the worst cases. She went blind and she lost all control of every function in her body, and it did eventually lead to death. But because this disease is typically not seen as fatal, this might be an experiment that would be set up as follows. Let's say somebody has this drug that they believe will help minimize the symptoms of a person who has MS. Now, initial, let's say you got a call, let's say you live every day in pain and you manage your pain, but your quality of life you wish could be so much better. So you get this phone call out of nowhere and someone promises you this magic pill that's going to make you feel better. The initial feeling you get is probably hope. And hope is a powerful drug. So patients that have this hope, they feel better even if you haven't even started the treatment yet. So the placebo effect is about somebody with this hope alone feeling better and then skewing the results because they're reporting that they feel better because they have hope. So the placebo is what we do as a control group. So in this case, we would set up half the patients that were selected for MS, randomly selected, single blind. The patients do not know that they have been placed into a placebo group versus a treatment group. But me, as the person conducting the experiment, does know which group is which. So that's why it's called single blind. Only the patients don't know that there's even a control group. So I give half the patients the control group, the whole control group get the placebo, which is usually like a sugar pill. It has no effect whatsoever. And then the other half is in the treatment group and they get the pill. Now that levels the playing field and neutralizes hope or any other kind of a variable such as that. And now I can see whether my drug really is helping the symptoms of MS more than their everyday life. A double blind study is needed sometimes. So, in the last example I just gave you, that was single blind. But in a double blind study, it means that not only the patients are blind, but so is the person conducting the experiment. So, for example, let's say I wanted to show that listening to music while taking exams is helpful for students to do better. So, students show up, I randomly assign them a room to take their exam. Half this class shows up in one room where it's silent and they take their exam, and the other half of the class shows up in their other designated room and there's some music playing in the background. They don't think anything of it. They're blind to the fact that they're in a room with music and the other half of the class is in a room that's silent. They take their tests. Now, I need to make sure that when I grade these exams, I am also blinded to which student is in which room. Because if I know which group of students were in the music room, and here I am trying to show that music is more helpful when taking exams, then I might be biased when I grade the exams. I might grade them a little lighter so they get better grades in the music room and much harsher in the quiet room. So this would definitely be called for a double blind study where I'd need to get a neutral third party person to split up the groups, administer the tests, collect the tests, shuffle the pile, and then give me the pile of these tests where I have no idea which ones were from which room. Bias is really important for you're going to hear this a lot throughout statistics. And bias has to do with the tendency to overestimate or underestimate the value of a certain population parameter. Essentially, it's having an opinion and then imposing your opinion in your experiment somehow. So, like I was talking about those survey questions, if you're saying the survey questions and you inserted your opinion into the question, you have inserted bias. If I collected those tests and I did not have a third party, so I knew which tests came from the music room and which ones came from the silent room, I could impose bias on the music room tests as I'm trying to get them better grades. So bias is always going to affect our data. The better experimental designs we have, the less bias we'll have in our results. And the more conscious we are about the way that we carry ourselves throughout an experiment or an observational study, the less bias that we can account for. All right, well, that, my sums up 2.1 Lords of Data, and I will see you for the next section.